Welcome back for another deep dive.
Yeah.
Today we're going to be diving into something that is both bizarre and fascinating to me, at least.
Hmm.
And that is the idea of parallel universes.
Oh,
We're going to be talking about quantum physics.
okay.
And I know quantum physics can sound intimidating,
Yeah.
but trust me, you don't need a PhD to grasp some of the core concepts that we're going to be talking about today. The goal is to just understand enough to be like, wow, that's really weird and interesting and kind of cool.
Right.
So we'll be talking about things like the double-slit experiment. We'll be
Oh.
talking about how simply observing something can actually change its behavior, which is
Yeah.
just crazy. But before we get too far, I would love for you to introduce yourself to the listener and let them know why you're the perfect person to be talking to us about this today.
Well, thank you for having me. I'm a theoretical physicist, and I've spent most of my career fascinated by the mysteries and the paradoxes of quantum mechanics,
Okay, fantastic.
and particularly interested in the implications of these things for our understanding of reality.
I love that.
Yeah.
So let's jump right in
Yeah.
to this idea of parallel universes.
Hmm.
I think most people, when they hear that, they immediately think of science fiction, right?
Right.
Like, is this really a thing?
Yeah.
Like, does it even make sense to talk about?
Right.
But parallel universes are actually a serious topic of discussion within the scientific community.
Absolutely. And the reason for that is because they emerge quite naturally from some of the most widely accepted interpretations of quantum mechanics.
Okay, so it's not just science fiction. It's actually based on some real scientific
It's not just some wild idea that someone came up with.
So let's talk
But it's a
about...
consequence of our best theory.
Yeah, let's talk about one of the most famous experiments in quantum physics, and that is the double-slit experiment.
Yes.
Can you explain to the listener how this experiment works? Maybe we can start with something that everyone can kind of grasp.
Right.
Like marbles, for instance.
Sure. Yeah. So imagine you have a wall, and in this wall, there are two slits. And now we start throwing marbles at this wall. Some of the marbles will go through the slits, and some of them will just hit the wall. Now, if we look at the pattern that the marbles make on the wall behind the slits, what would you expect to see?
I would expect to see two lines of marbles kind of like mirroring the two slits on the first wall.
Exactly right. You would expect to see two bands of marble impacts, each one directly behind one of the slits.
Okay.
Now let's change things up a little bit. Instead of marbles, let's use waves, like water waves, for example. So we have a similar setup. We have a wall with two slits, but now we're sending water waves towards these slits.
Okay.
Now what happens when water waves pass through the two slits?
Well, they probably make some sort of wavy pattern.
Right, yes, exactly.
Yeah.
You get what we call an interference pattern. So the waves that they pass through both slits simultaneously.
Okay.
And then they interfere with each other on the other side. And this creates a pattern with areas where the waves reinforce each other, so you get these high peaks, and areas where they cancel each other out, so you have these low troughs or valleys.
Interesting.
And this is a very distinct pattern that is characteristic of waves. So now we have marbles acting like particles, and we have water waves acting like waves.
Right.
Now let's introduce the star of the show, the electron.
Okay.
Now electrons are tiny subatomic particles, so much smaller than atoms. So if we fire electrons at our wall with two slits, what would we expect to see?
Well, based on what we've talked about so far, I would assume that we would see two lines, just like with the marbles.
That's what classical physics would predict. But here's the mind-blowing part. What we actually observe is an interference pattern, just like we saw with the water waves.
Wait, what? So you're saying that these electrons, tiny little particles, are behaving like waves? How is that possible?
That is the million-dollar question. It seems that each electron is somehow going through both slits at the same time, even when fired one by one.
So an electron can be in two places at once?
It's as though the electron is spread out like a wave interacting with itself to create that interference pattern.
That is so bizarre.
And this is what we call wave-particle duality.
Okay.
The idea that quantum objects, like electrons, can exhibit the properties of both particles and waves.
So it can be both a wave and a particle at the same time?
It can act like a wave, and it can act like a particle depending on the situation.
Depending on how you look at it or something.
Well, and that brings us to...
Yeah?
the even weirder phenomenon called the observer effect.
The observer effect.
Yes.
So explain what that is.
Okay, so imagine we now want to figure out which slit each electron actually goes through.
Right. We want to catch them in the act.
So we add a detector
Okay.
to observe the electrons as they pass through the slits. But here's the truly mind-boggling part. The moment we add the detector, the interference pattern vanishes.
What?
Instead, we get those two distinct lines that we would expect if the electrons were just particles passing through one slit or the other.
So just by adding a detector
Just by
and
adding
observing it,
a detector,
by trying to measure which slit the electron goes through,
we changed how it behaves.
we seem to force it to choose one path or the other.
It's like they know we're watching.
It's as if our observation is influencing the behavior of these electrons.
That is wild. So what's going on here? Is our observation actually creating reality? Or is there something else going on? And I think this leads us nicely into the many worlds interpretation.
Exactly. This is one of the many mysteries that the many worlds interpretation attempts to explain.
Okay, perfect. So let's talk about that next.
Okay, so the many worlds interpretation, it suggests that reality is a lot more expansive than we might imagine. It suggests that every time a quantum measurement happens, every time a particle could go this way or that way, the universe splits.
Okay, so instead of the electron going through the left slit or the right slit, you're saying the universe splits into two. One where it went left and one where it went right. Are you saying there's like a copy of me in each of those universes? Yeah, that's the idea. So in one universe, the electron goes through the left slit. In the other universe, the electron goes through the right slit. And yes, there would be a version of you in each of those universes.
Whoa, okay. So how does this idea of the many worlds interpretation address this observer effect that we were just talking about?
Well, the really cool thing about the many worlds interpretation is that it gets rid of this idea that the observer plays some special role, in collapsing this wave function that we talked about. So instead of just one possibility becoming real and all the other possibilities disappearing, all of the possibilities become real.
At the same time.
Yeah, but in different universes.
So it's like every time we make a measurement,
yeah.
every time we observe something, the universe is splitting into all these different
Exactly.
parallel realities.
It's constantly split.
And so one universe, I'm having this conversation with you about parallel universes, and in another universe, I decided not to do this podcast, and I don't know, doing something completely different.
Yeah, exactly. Maybe you're a musician or an artist or a chef.
Or all of those things at the same time.
Maybe you're all of them at the same time in some other universe.
I love that. So you mentioned something earlier about this idea that the many worlds interpretation avoids adding, you said, extra assumptions to quantum theory. Can you explain what you mean by that?
Right. So there are other interpretations of quantum mechanics, and some of them try to explain what's going on with this measurement problem by kind of introducing new rules or new concepts.
Okay.
And one example is something called the Copenhagen interpretation.
Mm-hmm.
And the Copenhagen interpretation says that the wave function collapses when a measurement is made. But it doesn't really say what exactly counts as a measurement or why this collapse happens.
So it's kind of like it just says, okay, something happens.
It just kind of happens.
And we don't really know why.
Yeah, it's kind of vague.
Yeah.
But the many worlds interpretation, it's different. It says, look, the equation that describes how these quantum systems behave, that's all you need. You don't need any extra rules. You don't need this wave function collapse. The universe just keeps branching into different possibilities, and that's it.
So it's like it's a simpler explanation in a way.
Yeah, it takes the strangeness of quantum mechanics and it just runs with it.
Okay, so you mentioned the Copenhagen interpretation. Can we talk a little bit more about what that is? Because I think it's kind of like the main alternative to this many worlds interpretation.
Yeah, so the Copenhagen interpretation, it's been around for a long time.
Okay.
And it's kind of considered the more traditional view of quantum mechanics. And it says that quantum systems exist in this superposition of states. It means that they're kind of like in this probabilistic haze of possibilities until you make a measurement.
Yeah.
And then the act of measurement collapses the wave function and you get a definite outcome.
So it's like saying the electron is potentially going through both slits at the same time?
Yeah, it's not really in any definite location until we measure it.
Until we observe it, and then it's like, okay, I guess I have to choose now.
Right, exactly.
But does the Copenhagen interpretation explain, like, how this collapse happens?
That's actually one of the things that people debate a lot.
Yeah.
It doesn't really give you a mechanism for this collapse.
So it's kind of another one of those things where it just says, it happens.
Yeah. And some physicists are not very happy about that because it leaves these questions open, like what exactly is a measurement?
Right.
And why does this act of observation seem to have this power to collapse the wave function?
So are you saying that you prefer the many worlds interpretation over the Copenhagen interpretation?
Well, I have to admit, I find the many worlds interpretation very elegant.
Yeah.
And I kind of like that it just takes the equations as they are and doesn't add anything extra.
Yeah, and it definitely provides an explanation for why the observer effect happens.
Yeah, it does. It says that the observer is not really doing anything special. The universe is just branching, and the observer is just going along for the ride.
Okay, so it's like each observer is only aware of the branch of the universe that they're in. Okay, so we've talked about the double-slit experiment. We've talked about the observer effect. We've talked about the Copenhagen interpretation, the many worlds interpretation.
Mm.
I think we're starting to get a pretty good grasp of these different ideas and how they fit together.
Mm.
So let's shift gears a little bit and talk about the implications of all of this. Like, how does this idea of parallel universes, if it's true, how does it change how we view our own lives and our choices?
That's a great question. And I think it really makes us think about the meaning of free will. Like, if every choice we make creates a new universe where we made a different choice, does that mean that all possibilities are actually realized somewhere out there in the multiverse?
Yeah, it's like, are we actually making choices or all the choices already made? And we're just kind of experiencing the different branches of reality where those choices have been made.
It's a mind-bending thought. And it also makes you wonder about all those other versions of ourselves. Like, what are they doing right now? Are they living out our dreams? Or are they facing challenges that we can't even imagine?
It's like an existential choose your own adventure.
Exactly. And it raises some really interesting ethical questions. Like, if there are countless versions of ourselves out there, do we have any responsibility to them?
It's like asking if we have a duty to the unrealized possibilities within ourselves.
It's a deep philosophical question, and I don't think there are any easy answers.
I feel like the more we learn about quantum mechanics, the more questions we have.
Yeah, it's definitely a field that raises more questions than it answers.
Like every time we think we're starting to understand something, it just opens up a whole new can of worms.
Yeah, and I think that's part of what makes it so fascinating.
Yeah, it's definitely fascinating, but it's also kind of frustrating
Right.
because it makes you realize how much we don't know.
It really does.
Like how much is there that we just haven't even thought of yet?
Well, it makes you question whether we even have the right tools to think about it.
Yeah, that's what I was just thinking.
You know, our language,
Yeah.
our concepts, like, are we even equipped to describe this quantum reality?
Yeah, like we're using words like particles and waves and observations. But do those words really even make sense?
Right, they're based on our everyday experience.
Yeah.
Which is governed by classical physics. And when we try to apply them to the quantum realm, it's like, it doesn't quite fit.
It's like trying to describe a color that no one has ever seen before.
Exactly. You just don't have the words for it.
So how do we even begin to talk about these quantum phenomena if our language is inadequate?
Well, maybe we need a new language.
A quantum language.
Yeah, quantum
I
language.
love that. What would that even look like, though?
Well, it would have to be a language that can embrace these concepts of superposition and entanglement and non-locality.
Yeah, those are definitely not words that we use in our everyday conversations.
Right. Maybe it would involve more visual representations or mathematical symbols, or maybe it would borrow from poetry and music.
Quantum poetry, I love it.
Yeah, why not? If we want to truly understand the quantum world, I think we need to be open to new ways of thinking and communicating.
I think you're absolutely right. Well, on that note, I think it's time for us to start wrapping up this deep dive into quantum physics and the idea of parallel universes. Is there any kind of final takeaway that you want to leave the listener with?
I guess if I had to sum it all up, I would say that the universe is far weirder and more wonderful than we could have ever imagined.
Yeah, I think that's a good way to put it.
Like quantum mechanics, it just throws all of our classical intuitions out the window.
Yeah, it really does.
And it forces us to reconsider what we think is possible.
And to be open to the possibility that there might be other universes out there where things are completely different.
Exactly. And who knows, maybe in some of those universes we're having the same conversation right now, but with slightly different outcomes.
I like to think that there's a universe out there where this podcast is super popular.
Yeah, me too.
Uh-huh.
And one where we've solved all the mysteries of quantum mechanics.
That would be amazing.
Uh,
Well, I want to thank you so much for joining me on this deep dive into quantum weirdness. I've learned so much, and I hope our listeners have too.
It's been a pleasure. And remember, keep questioning, keep exploring, and never stop wondering about the universe and all its possibilities.
That's great advice. And to all of our listeners out there, thank you for joining us on this journey. We'll see you on the next deep dive.